In this video, we'll finish up Chapter 6. We'll talk about the general rule for computing probabilities combined using ANDs. We'll talk more about conditional probabilities. We'll cover the two types of error, and we'll talk about independence of events. In the four stages of statistics, we're talking about probability, and we're still finding probabilities. Let's recap. If two events, A and B, are mutually exclusive, that is, they can't both happen at the same time, or they're non-overlapping, we can find the probability of A or B by adding the probabilities of A and B. If A and B are independent, that means that whether the first occurs has no bearing on the probability of the second. We can compute the probability of A and B by multiplying the probabilities of A and B. In general, for arbitrary events A and B that might overlap, we modify the OR rule by subtracting from the sum the probability of both events occurring simultaneously. Now we've generalized the OR rule. Now we need to find a generalization of the AND rule that covers the possibility that A and B are dependent. In the last lecture, we saw this example. In a child's pocket, there are 2 quarters and 2 nickels. If the child randomly picks a coin and then without replacement picks a second, what is the probability that both coins are quarters? We can't simply multiply because the probability that the second one is quarter depends on what the choice was the first time. If the first coin selected was a quarter, then the probability that the second one is a quarter is 1/3, because there's 1 quarter left out of 3 possible choices. If the first choice was not a quarter, but was instead a nickel, then the probability that the second one is a quarter is 2/3, because there are still 2 quarters left out of 3 coins total. So, this diagram shows you that there are 4 choices for the first selection: quarter, quarter, nickel, nickel. And for the second selection, the probabilities depend on which coin was selected and removed from possibility. The probability that the first one is a quarter is 1/2, and then the probability that the second one is a quarter is either 1/3 or 2/3, depending on the first coin selected. Conditional probability is a term that we use when we're working with 2 events and we want to know, for example, the probability of the second event given that or assuming that the first event has already happened. Notationally, we'll write this as the probability of B given A. That's the probability that B happens given that A has already happened. Another way to denote this that you'll see is the probability of B, and then a vertical bar to indicate the given, and then A. We'll use conditional probabilities to deal with dependent events. So, let's look at the kid with the coins again. What is the probability that both coins chosen are quarters? The probability that the first one's a quarter is 2 out of 4. The conditional probability that the second is a quarter, given that the first was a quarter, is 1/3. So, of those 2 times out of 4, moving forward, 1 time out of 3 will have a quarter. So, we multiply 2/4 times 1/3, which gives us 1/6. Let's look at this in a diagram. Here you see all of the possible choices of 2 coins. Here we're differentiating the 2 quarters by labeling them Q1 and Q2, and we're differentiating the 2 nickels, N1 and N2. You can see that there are 12 possible outcomes. Now, Of those 12 possible outcomes, and here we're looking at these as pairs, so N1 and N2 together is one possible outcome. And because we're differentiating between the two, that outcome is different from N2 and N1, because we're keeping track of which one comes first. So of these 12 possible outcomes, 6 of them, in the green oval, involve picking a quarter first. So now if we restrict ourselves to looking just at those 6 outcomes, 2 of the 6 in the pink oval involve choosing a quarter second. So altogether, 6 out of 12 times 2 out of 6, that's 2 of the 12 outcomes, show both coins are quarters. Let's look at this on a two-way table. Here we have students surveyed and classified by sex and whether or not they have their ears pierced. Compute the following probabilities: the probability of being male, the probability of having ears pierced, given that the student is male, and the probability of being both a male and having ears pierced. The probability of being male we can compute by looking at the fact that there are 200 males total out of 500 students total, so the probability of being male is 200 over 500, which is 0.4. Now, the probability of having ears pierced given that the student is male means that looking at the given the student is male part, here it's the given M, that means we're only looking in the male row. Within the male row there are 200 students, 20 of whom have ears pierced. So the probability of E given M is 20 out of 200. The probability of M and E, that is the probability of being male and having ears pierced, and this is not a conditional probability. We're looking at this one particular group that has 20 people in it, males and ears pierced, and we'll divide by the total number of people, that's 500, to get 0.04. Notice that the probability of being a male and having ears pierced is computed as the probability of being male times the probability of having ears pierced given that the student is male, which is 0.04, but the probability of being male and having ears pierced is not the same as the probability of being male times the probability of having ears pierced. That multiplication rule depends on the events being independent. Since these events are dependent, we get a different number. Here's our rule. Given any two events, A and B, the probability that A and B both occur is the probability of A times the probability of B given A. Remember, when you see the word and, you want to think multiplication. Now, how does this differ from our original and rule? Remember, it said the probability of A and B is equal to the probability of A times the probability of B. This term that is underlined with that little blue bracket has been changed from the probability of B to the probability of B given A. It's important to note that these two rules are the same because the probability of B given A is equal to the probability of B if A and B are independent. Remember that independence means that the occurrence of one does not affect the probability of the other. So the probability of B would be the same no matter if A occurs or doesn't occur. Here's an example. Studies suggest that lie detector tests are well below perfection. 80% of the time, the lie detectors conclude correctly that someone is a spy when they actually are. 16% of the time, they conclude that someone is a spy when that person actually isn't. Let's assume that 10 out of 10,000 government employees are spies. Do you think the overall probability of being detected as a spy, P of D, again, whether you are or not, so the probability of D is the probability that a person is identified as a spy by the lie detector, either correctly or incorrectly. Would we expect that probability to be closer to the probability of detection given that the person is actually a spy, which is reported as 0.8, or the probability of detection given that they are not a spy, which is reported as 0.16, which is closer to the actual detection probability? The secret here is in the relative number of spies. Because so many of the employees are not spies, we would expect the true probability of detection to be close to the probability of detection given not a spy, because that event, not a spy, happens far more often. In fact, we can compute that the probability of detection in this case is 0.16064, very close to 0.16. Here's another rule that derives from the general AND rule. Remember, the general AND rule says the probability of A and B is the probability of A times the probability of B given A. If you divide both sides of this equation by the probability of A, we get this rule for computing conditional probabilities. The probability of B given A is the probability of A and B divided by the probability of A. Let's see an example of that rule in action. Here we're looking at the lie detectors again. Let's say that the probability of being a spy is 0.001. The probability of a spy being correctly detected is 0.8. The probability of a non-spy being incorrectly detected is 0.16. The probability of being a spy and being detected is 0.0008. The overall probability of a positive lie detector test is 0.16064. So let's say that the lie detector indicates that an employee is a spy. What is the probability that he actually is a spy? Well, our rule says that the probability of being a spy given a positive lie detector test, that's probability of S given D, can be computed as the probability of D and S, which is 0.0008, which, by the way, was computed from these first two lines, multiplying together, divided by the probability of D, which was given as 0.16064. So, if an employee gets a lie detector test and it indicates that that employee is a spy, the probability that that person actually is a spy is 0.00498. That's a little bit less than half of 1%. Notice how different that is from the other conditional probability. If you switch the order, the probability of detection given that you're a spy is 0.8, but the probability that you're a spy given that you are indicated is less than half of 1%. This is an exercise in what's called Bayesian probabilities, because Bayes' theorem uses these conditional probabilities to find the probability of an earlier event given what happens later on. As we saw in that previous example, there are two types of error that we can see in the lie detector test. The type 1 error is concluding that an employee is a spy when that person actually isn't. You can think of this as a false positive. The type 2 error is the opposite. It's at concluding that the employee is not a spy incorrectly when that person actually is a spy. That's a false negative. Let's look more closely at those two errors. Remember, for the lie detectors, we have the probability of being detected if you're a spy is 0.8. The probability of being detected if you're not a spy is 0.16. What is the probability of a type 1 error and the probability of a type 2 error? Well, the type 1 error, it's given to us. That's the probability of being detected given that you are not a spy, so that's 0.16. The type 2 error, we have to do a little bit of work to find. A type 2 error would be the probability of not being detected given that you were a spy. We know the probability of being detected given that you're a spy, and that's 0.8. So we'll subtract that from 1 to get 0.2. That's the probability of the type 2 error. Let's talk more about independence of events. Anytime we're talking about whether two events are independent, we're talking about conditional probabilities. This is something that comes up a lot in statistics when we're looking for a dependence or a relationship between two variables. Let's look at an example about conditional probabilities. Here's a two-way table we saw earlier relating gender to ear piercings. Should these two variables be dependent or independent? If they're dependent, which one would you expect to be less? The probability of E given M or the probability of E? Remember, the definition of independence says that those two probabilities, probability of E given M and the probability of E, those two probabilities will be equal if those events, E and M, are independent. And what are those probabilities? Which one is smaller? If there's no relationship between gender and ear piercings, that is, if these are independent, then the proportion of females with ears pierced should be the same as the proportion of males with ears pierced. But you notice that the proportion of females with ears pierced is 270 out of 300. That's females with ears pierced out of total number of females. Whereas the proportion of males with ears pierced is 20 out of 200. That's much less. So we conclude that these are dependent. Because so many fewer males have pierced ears, I would expect that the probability of having your ears pierced, given that you're a male, is less than the probability of having your ears pierced overall. And if we compute those probabilities, the probability of E given M, as we said before, is 20 over 200. The probability of having ears pierced in general, that means we're looking at the totals, that's 290 over 500, which is 0.58. Sure enough, the probability of E given M is quite a bit less than the probability of E. Now take a look at this table. Here we're looking at students classified according to gender and whether or not they get an A in statistics. Should gender and getting an A or not be dependent or independent? How should those compare? After we guess, let's actually compute the probabilities and see how they compare. Ideally, your gender won't affect the likelihood of you getting an A. So, we would expect those two probabilities, the probability of getting an A and the probability of getting an A, given that you're female, should be the same. Let's see. The probability of getting an A overall is 0.25. We can read that right out of the table, since these are already in proportions. Now, where would we find the probability of A given that you're female? Well, that one we have to compute a little bit. 15 percent of the total students represented in the table are females who get A's. 60% are females. So to get the proportion of, or the probability of getting an A, given that you're a female, we'll take the probability that you are female and got an A and divide by the probability that you are female. That's a rule that we saw just a little while ago. When you divide, you get 0.25. Those two numbers are the same. We conclude that these are independent. To generalize those last two examples, events A and B are independent means that the probability of B and the probability of B given A are the same. So if we want to test for independence, we compute those probabilities. If they're equal, then A and B are independent. If they are not equal, then A and B are dependent. So independence is equivalent to the statement that the regular and the conditional probabilities are equal. This ties back into our computation for tables of expected counts. Remember that if A and B are independent, then the probability of A and B is the probability of A times the probability of B. That means if A or not A is independent of the variable B or not B, then the count in A and B must equal the total of A times the total of B divided by the overall total. That's exactly the computation we used in the previous chapter to compute tables of expected counts. Here's an example. Here we see the two-way table for gender and ear piercings again. On the right, we see the actual one that we've been working with. On the left, we see the table of expected counts. How different are these? Well, we see big differences, especially if you look in the male row for pierced. 116 versus 20, there's a big difference. For females, that is not male, and not pierced, we would expect 126 if they were independent, but we actually only see 30. Those differences are huge. That indicates that there is quite a strong relationship between these two variables. So again, remember that we compute this table of expected counts by multiplying the row total times the column total and dividing by the total of the totals. Now let's look again at this table of relating gender and grade. On the right we see the actual observed values, and on the left we see the computed table of expected values. What's the difference here? Well, there's none, because gender and grade are not related. To wrap up, we considered the general AND rule. We looked more deeply at conditional probabilities. We talked about type 1 and type 2 errors. We talked about independence of variables. We talked about how to test for independence of variables. And we found a rule for independent events. We also talked about creating a table of expected counts if variables are independent.